Now, let's move on to the topic of this chapter, which is torsional loading. So what you're gonna do is we'll repeat 1 through 7 of axial loading for torsional loading. That's it. And before talking about torsional loading, let's think about what is the technical relevance for torsional loading. So in designing electric cars or designing like a small toy cars, you have to use motors. Or if you want to use a gasoline car instead of motor, you have to use engines. So whether you are considering motor or engine, both of them are changing the energy to make a rotational motion, and by transmitting that rotational motion and rotation energy, you can move your car. Okay, for that you have to use gears and transmissions and etc. Okay, so one of the most popular use of torsional loading can be found here, and you can see here that circular shaft is widely used to transmit powers through torque. Then what you can expect here is the shaft is deformed under torsion. What I mean by torsion is torque about the rotating axis. Okay, so our textbook use this curved arrow notation, but there are many other textbooks which uses double arrow notation. Okay, so instead of this curved arrow notation, if you use double arrow notation, you can apply most of the knowledge you have learned in axial loading for torsional loading chapters. Okay, so whether you use double arrow notation or curved arrow notation, yeah, it completely depends on you. And I'm gonna tell TA that even though students sometimes use double arrow notation, yeah, you can just grade it equally with curved arrow notation if the answer is right. Okay, so depending on your convenience, choose whatever notation you want. Then before talking about the kinematics and force and torque analysis, let's discuss about some observations on torsionally deformed circular shaft. Yeah, it is really important to have circular here. Okay, so without proof or mathematical discussion, yeah, we'll assume these four as true in our chapter, which gonna help us to make mathematical analysis and physical analysis easy, and rigorous proof about these assumption will be provided in stress analysis course or solid mechanics course, second solid mechanics course for undergraduate or advanced mechanics course in graduate schools. Okay, so the assumptions and observation on torsionally deformed circular shaft are following. First, long axis remains straight and not changing the length. Second, each cross-section remains planar and perpendicular to the axis. Third, cross-section may rotate but do not distort, remain completely circular. Yeah, think about like these circular shaft, and if you imagine a cross-section here, and even though you add this kind of torsion, these originally planar cross-section remains planar without distortion, and relative rotation between two cross-sections is proportional to their distance along the axis. Suppose that you take like x1 position here and x2 position here, and after you exert torsion to this circular shaft, you can expect that the originally located here, the original point moved to here, and originally located point here will move to here. Okay, and you call this as twist angle phi 1, here twist angle phi 2, and if you define delta x as x2 minus x1, this is delta x, and if you define delta phi as phi 2 minus phi 1, so it will be, this will be delta phi. Okay, then fourth observation says that delta phi is proportional to delta x. Okay, so this is quite strong condition, right? So whether you take these 2 points, whether you take these 2 points, like the degree of the way they deform is really uniform over the entire sample, so that this twist angle delta phi is always proportional to this relative distance. Okay, so these are the 4 observations that and 4 assumptions we're gonna make in our chapter without making mathematical proof. Okay, mathematical proof of that will be provided in later courses. So and you have to remember that these observations are only valid when the cross-section is circular. If you imagine a square cross-section, it will change the shape after torsion. You may have tested it using your rubber erasers, maybe when you are young. Second, a length is at least a few times larger than the diameter. Okay, so please remember the Saint Venant's principle. Something similar happening here. You have to have length which is quite larger than the diameter to have these assumptions true. Then shear strain is sufficiently small, I mean linear asymmetry. Okay, if this A, B, C are true, then you can believe that 1, 2, 3, 4 observations are true. Okay, so most homework problems that you're gonna see our torsion chapter will have A, B, C true, so that you can use and you can believe 1, 2, 3, 4 is true for our chapters. Okay, so having this in mind, let's move on to real meat of the today's course. So today we're gonna cover 2 topics. First, I will discuss about the analogy and difference between torsion and axial loading. And in the second chapter, we'll talk about stress for other orientation. This is something we have done for axial loading when we discuss about stress on oblique plane. Okay, so we can do same thing here for torsional loading. So let's try to make a one-to-one correspondence between axial loading and torsional loading. So in axial loading, we consider the force P and displacement delta as a response to force, and we consider original length L. And regarding the displacement delta, we learned that displacement is proportional to length of the beam and proportional to force, and it's inversely proportional to cross-sectional area A, and it's also inversely proportional to Young's modulus, so that delta turns out to be PL over AE. So we're gonna have a similar conclusion about this torsional loading. Here you can we're gonna set gamma as a shear strain on the surface. Okay, so this is gamma, and we call twist angle as phi here. So originally located here, but after torsion, this green point moved to here, and you measure this angle, and we call this as twist angle. So this twist angle, we'll see that it is proportional to length L. It is proportional to torsion T, which is torque about the rotating axis. This will be inversely proportional to polar moment of inertia. This is gonna be geometrical vector, and it will be inversely proportional to shear modulus, because we are considering shear strain, right? So originally, suppose that originally the pillar has this stripes. After torsion, the stripe will have like this oblique orientation. Now, what you're gonna prove is that twist angle will be proportional to torsion T, length L, and geometrical vector J, inversely proportional to J, and inversely proportional to shear modulus G. Okay, so this will be the conclusion of our first topic of today's lecture, and we're gonna get into the details of today's first topic in the next video.